Hi, this is Physics 2, and it's chapter 26 for Relativity. And this will be part 1. Not sure exactly how many parts I'll have. So we're going to start off. If you remember, if you take in Physics 1, which I would recommend that you have done, um, you saw early on us discuss what's called the reference frame. And for the most part, we look at reference frame as coordinate system. So we can just look at right now y and x. And we measure based on the reference frame for a particular object. So for example, if we have a car that's moving, we may set the reference frame from location A, and then that car is moving, and as it gets farther away over, well, we'll call this time, and y will be the distance away from it. As it gets farther away over time, we get a linear graph if it's moving at a constant speed. But we may be looking at something, that's point A. Maybe if we are at point B, we actually see this thing getting closer over time. Okay, or point A is over here. Okay, and we can think of this as, okay, just say this is school and this is your house. You're driving home from school and towards your house. But if this is your house and you're driving home from school, you get closer to your house. Okay, so it's two different kinds of frames of references. So, if we're in a car here, we measure our speed, we can measure it relative to a car. And so the person is actually at rest in a moving car. And so the car and the person move together, and they're traveling technically at the same speed, because the speed of the car is going to be measured to the ground. And so the person's speed is the same as the car measured to the ground. But measured to the car, it's zero. They're not moving away from that car. They're staying with that car no matter what. Well, maybe not no matter what, but they're staying with that car. And so, if you had another car passing that car, that car's speed could be measured relative to the car they're passing, and vice versa. And so there's different frames of references. We have what's called an initial frame of reference. And this is where the frames of reference have Newton's laws that are valid. His laws of forces for F equals ma. What's the other ones? Law of inertia, and equal and opposite reactions. So if we look at an example where we have a ball and a merry-go-round, and the ball will start to move outward even though there are no forces on the ball, right? So if you have a merry-go-round, and it could be any kind of what do you call it, things that have the horses, or you can just look at one of those things that you have where they have places to hold on to and kids love spinning it around. You have a ball here, it's going to be forced to the outside as this thing spins, even though there's no actual force forcing it to the outside. And so this is not an inertial reference frame. Okay. Best way to know, accelerated objects are not in an initial reference frame. So if there's an acceleration, then you're not looking at one where it's an initial reference frame. So there has been some assumptions that we make that are based on reference frames and based on experience. So lengths of objects are the same in all reference frames. Okay, this is something we're assuming. Time passes at the same rate. Mass of an object does not change. Forces are unchanged by change in initial reference frame. And acceleration is also the same in all reference frames. So distance and velocity can change based on reference frames, but the acceleration is the same. All right, so the speed of light is a velocity, right? And the speed of light is v. I'll put light down here. Speed equals 3 times 10 to the 8th meters per second. And so it should change when the initial reference frame changes. But this is not the case. The speed of light always remains that 3 times 10 to the 8th in all initial reference frames. So in the 19th century, they predicted that there was this ether in which light travels through at a speed measured to that frame of reference. They actually set out to prove this, and Michelson and Morley created an interferometer to prove the ether existed. They ended up proving that it didn't exist, and so they actually proved the opposite of what they actually intended to. Which left them with more of a conundrum than they wanted. It's one of the few times that you prove something and then end up with more questions than answers because what you wanted to prove was the opposite. Right, so this led to postulates of special theory of relativity. The first postulate is the laws of physics have the same form in all initial reference frame. This means that no experiment that can be done in an initial reference frame that can show you if you are at rest or moving with constant velocity. So basically, there's no way you can prove within your reference frame if you're at rest or moving with a constant velocity. For example, if we look at the forces on a person that's just sitting down. Right, so the person sitting, they have their normal force from the chair, and they have the weight as they sit down acting on the chair. Right, we know that if we look at this, this is equal and opposite forces. But the question is this person really sitting and at rest, or are they still moving? Well, to us, from our reference frame, we would say that they're resting. Then if you go out of your reference frame, you see that they are actually on the earth on one spot, and this is spinning around. So this is spinning. And then if you say, well, the earth could be at rest, but the earth is revolving around the sun. Right? And so, at this point, you have to go beyond your reference frame to see if you are really moving at constant velocity or to see if you are resting. And then the second is light propagates through empty space with a definite speed c, independent of the speed of the source or the observer, meaning the speed of light would be the same even if we were moving towards the source, away from the source, which is opposite of the Doppler effect, which we have learned about in chapter 12. And so the speed of light would be the same at rest, even if something is at rest as well. So this led to some experiments that were more of, I guess you can say, thought experiments to a point. One idea that came up from this is this idea of simultaneity. And this is that an event, something that occurs at a specific place and time, doesn't always happen to everybody at that same time. So in this first experiment, light strikes two different places at the same time. So light strikes A and light strikes B. A person midway between these two will see light strike A and the light strike B. Right? And if we look at it, we know the light travels at the speed of light. So as this light travels from A to O, it's going to travel at the same speed. And this distance from A to O is the same as O to B. So it's going to take the same time. Okay, remember, time, well, I'll write it this way. Velocity is distance over time. So time is distance over velocity, which I have here. The distance A to O over the speed c is equal to the distance B to O over the speed c. So this means that the time is going to be equal on both of these. So this person here at O is going to see A happen and B happen at the same time. In experiment 2, the lightning strikes. What did it do? I swear it's just the W didn't show up. Two different places at the same time, points A and B, but a person is halfway between A and O. So in other words, this person is over here now, okay? And we could have made it over here, it doesn't matter really. But basically, it's this person's anywhere else but at O. But we're going to, I'm going to draw it here. Say the person's between A and O. And the lightning strikes. It really doesn't look like lightning, but well, that looks a little bit better. So lightning strikes same time at A and at B. So now we know the distance between A and the person and the distance between B and the person are not the same. So this distance, dA, is equal to 1/3 of the distance of B. Okay, so I'm going to put in another dot here. Whatnot. If we call this is 1/3, 1/3, and 1/3. So this is the whole distance of x, where the person is, to B, and then this is only 1/3 of that. Okay, because this is going to be equal to these, all three of these. So this is 1/3 of this distance. Another way of looking at it is we can just kind of put numbers in. If this is 1 meter, and this is 1 meter, and this is 1 meter, and this is 1 meter, the distance from X to B is 3 meters. Distance from X to A is 1 meter, 1/3 of 3. And then we can write it as 3dA equals dB as well. And so we can look at the change in time. The change in time, or the time it takes to go from X to A, is going to be, dA over C. And the time it takes to go from B to X is going to be dB over C, which is equal to 3dA over C. So it's going to take 3 times as long to go from B to X as it does to go from A to X. Okay, that actually makes sense. And so even though these are happening at the same time, this person doesn't know that. This person here does not know that these happen at the same time. He sees it. He sees this first. Then he sees this. And he would say, well, this happened first and then this one happened. But in reality, they really happened at the same time. Right. So this goes now into what's called time dilation. And so we get another experiment here. The ship is traveling across the Earth and sends a light ray from one side to the other in the ship, measuring the time it takes for the light ray to return. Right, so the light ray really is just going across the ship. Right, so assume that this ship is at rest. It's going across the ship and then back to the receiver. But if the ship is moving, it's going across the ship, but to get across the ship, it has to kind of follow this path because the ship is also moving. So it follows this path as it goes across the ship and then back to the receiver. Okay, and so D here is the width of the ship. L here is the length it moves when it moves across that width. Okay, and so this creates a triangle, and you have D as your width, L as your convex, and so using Pythagorean theorem, we get D squared plus L squared. And then we get the same thing on this back end side when it travels the next length. Because there's no reason I think it's going to go any longer in length when it's traveling the same distance across the ship. So you get D squared plus L squared and take the square root. This observer is going to see it kind of do this if he's able to see the light. If you're in the ship, you're going to see it do this, and even though you're moving and everything's moving, this is what you'll see if you're in the ship. This is what you'll see if you're outside the ship, and you're able to see into the ship. So if we want to find the time it takes, right? So we have what's called proper time, and we have what's, I guess you can call it relative time. So first, just looking at the time it takes to go across the ship and back. it has to travel, and this is light again, so it's traveling at speed c, but it travels two widths, so across and back, which is two distances, over speed c. Okay, so that's your distance over speed, gives your time. Actually, you know what? I'm going to see if I can get the picture of mainly in. Okay. So now in experiment B, the observer on the ground is measuring the time for the light, same light rate to travel across the ship. So he's seeing this again. And so here, he sees the light travel a distance 2 times this length. So light, we know this is the length of this hypotenuse here. But he sees it do hypotenuse going up and hypotenuse going down. So it's 2 times this. That's his distance. Well, L is half the horizontal distance. So L is equal to V times T, which is the speed of the spaceship. So, and the time it takes for the spaceship to go by. And so, for this, if T is the time it takes to go by completely, you're going to take half that time for it to go halfway, since L is half of that length. Or we can think of it as 2L as the time it takes to go the whole length. So that's why we're dividing it by 2 here. Right? And so this is the time it takes for it to go all the way across, and then we have to divide by 2 because L is only half the distance. And so we'll now find the time, the change in time, using those two distances. So that distance over that speed. And so I start with this. I substitute in for L, V delta T over 2. Since L is squared, those have to be squared. And then basically all I did here was square that 2, so I get 4 on the bottom. And then I multiply C over to this side, so I have the denominator gone. And then I'm going to square both sides. I did the denominator so it's easier to square. So I square both sides. And so when I work out the algebra here, I get 4 times d squared plus v squared delta t squared. So when I multiply this in, this 4 cancels with that 4. And let's see, I subtracted over this term here. I subtracted over to this side. And then I factor out the delta t squared. So I have c squared minus v squared. Then divided over the c squared minus v squared. So I have 4d squared over c squared minus v squared. And that's equal to, again, delta t squared. And then I factor out c squared. So I have 1 minus v squared over c squared. Right, and then the next step would be taking the square root. When I take the square root, I get on the top just 2d. Square root of 4 is 2. Square root of d squared is d. C squared becomes just c, and then I have the square root of this mess down here. But this is actually what it really is supposed to look like. Now 2d is, let me go back up a little bit. 2d is equal to that delta time over, I should say this, 2d over c is equal to that delta time. So that's where this 2d over c becomes just delta time. So we have delta time over square root of 1 minus v squared over c squared. This 1 minus 1 over 1 square root of 1 minus v squared over c squared we'll start calling gamma because it appears so much in relativity. And so you have delta t equals gamma delta t naught. And the delta t naught is considered proper time, or best way I like to think of it as the shortest time between two events. So for this case, that shortest time is going to be the time it goes straight across and back. Where this, since it's going a longer distance, it's going to take a longer time. And so this is going to be your kind of relative time. Right, so the way things are set up with this gamma, and we don't have to go too much into this table, but the way things are set with this gamma, you want your speed in terms of speed of light, so kind of a percentage of the speed of light. So that way it divides with that c squared, and you end up with just a 1 minus percentage, and then the math is a little bit easier. You don't have to worry about even remembering what speed of light is in that case. So a lot of times you'll see these, and we can see how gamma changes as you increase and get closer to the speed of light. Alright, so for time dilation, clocks moving relative to an observer are measured to run more slowly as compared to clocks at rest. So the time is measured to pass more slowly in any moving reference frame as compared to your own. And so it takes longer to, when the reference frame is moving, well, where if it's not moving, it doesn't take as long, so the time will be shorter. We actually see this in particle physics. We'll start talking about the muon, and they're able to measure it by speeding up the muon so it's closer to the speed of light. That way it starts to stay longer and take longer to decay because it decays really fast. I'll mention it again when I get to particle physics. Alright, so in this next experiment, let me actually erase that so I have a clean slate. Oh, there's pens over here. Right, you have an astronaut moves at 0.5 speed of light and spends 10 years moving through space before returning. How much time has passed on Earth? Right, so first let me write down an equation. So this is for 1. Delta t equals your change in proper time over your 1 minus v squared over c squared. Alright, so they're moving at speed of light, so your v is 0.5 c, and you're spending 10 years. So now, before I get to the 10 years, let's work out some of the math here. So delta t equals delta t sub 0 or the square root of 1 minus 0.5 c squared over c squared. And so this works out to delta t sub 0 over square root of 1 minus 0.5 squared. The c squares cancel. And so you get delta t 0 over square root of 0.75. And so now we can just get that as a fraction or as a value. So 1 divided by square root of 0.75 equals 1.15 roughly times delta t sub 0. Okay, so now the question is which t is that 10 years? Is it this one or is it this one? So this person is spending the time in space for 10 years. So that 10 years is how much that person spends in space. That's based on what he sees. So the proper time is going to be the 10 years. Since this is based on what that person sees. This change in time is going to be the time on Earth that passes. Okay, this is not what the person sees, but this will be what the person comes back to. And so what you get is 11.5 years. Okay. 10 times the 1.15 gives you 11.5. So based on his birth certificate, he will be 1.5 years older, but based on biology, he would be, only 1.5 years younger than what his actual age would be. So the idea is, if you're going fast enough, you get back, you may, pass 20, 40, 50 years, and only pass maybe 10 years. Right, so we can do the next one. The next one's very similar. An astronaut moves at 0.9 speed of light, spends 10 years in space. Same question, when does he get home? So very similar setup. And I'm not going to go through as much of the math as I did before because the setup's so similar. Right, C's cancel. We do 1 point minus the 0.9 squared, and the t proper is going to be the 10 years still. 10 years over square root of 1 minus 0.9 squared. We get 22.9. So if he left in 2020, when he's 10 years on space, when he gets back, it's going to be 2042. Now we're going to do it at 0.99c. Okay, so again, 10 years for the proper time. 1 minus 0.99c squared over c squared. So this would equal 70.9 years. Right, so if this guy left in year 2020, when he's 10 years older, it's going to be 71 years that pass. So it'd be like almost 2091. course, we're not taking into account part of it's going to be speeding up to this point, and then slowing down to this point. I think the idea is most of the trip that this person's in is going at that speed. Okay, I'm actually going to stop here so this video isn't so long. Probably give you time to digest what we just went through, because it's like out in left field for most people, and science sounds more like science fiction for pretty much everybody. What we're going to go into next is length contradiction or length contraction, which is very similar but also kind of the opposite of what we just did, in a sense. And then we'll get into, let's see, some space-time theory, and then relativistic momentum, and then ultimate speed, and some relative for energy and relative velocity, comparing two things that are moving. But this is probably going to be the very next thing this what we just did and this next thing that we're doing are probably the two most important things in this chapter. Okay, so I'll stop this here, and I'll see you in part 2.